Yes, recording has been started. So we can start now. So let me just talk about Leo. So Leo did his PhD at the University of Concepcion in Chile. After that, he joined ICFO, where he's part of Professor Antoniassin's quantum information theory group. He's one of the senior postdoc in the group and has a very good expertise in characterizing quantum systems through tomography from single to multi-quantum, multi-qubit systems. So today he's going to talk about some fundamental and but very important aspects of this topic. And so please feel free to stop him at any time and ask questions if you have any doubts. So we always encourage interactive discussions in this seminar. So please, Leo, you start.
Okay, thank you, Ali. All right, so today I want to talk about how to measure properties of quantum states. And in particular, I want to focus on quantum state tomography that gives us full information about the state, and also direct fidelity estimation that only gives us partial information. So those are the two topics I want to talk about today. Good. So the first thing we have to talk about is why characterizing quantum states is so important in quantum information systems. So quantum systems are unique in the sense that we can't observe their state in the same way we do with classical systems, right? Because if we have a quantum system and we measure it, we disturb it, and we only get a few bits of information. Then, if we want to know some property of the state, we have to measure some observable, but that process changes the state, right? And depending on the measurement we perform, we cannot use the state again to obtain more information. Okay, so this is where the different methods of quantum state characterization come. So since we cannot look at the system directly, we have to prepare several copies of the quantum state and infer information from repeated measurements. So the idea is to collect the data, post-process it, and then make educated guesses about the quantum state or some property of the quantum state based on that data, right? Okay, so why do we care about this? Well, characterizing quantum states or knowing properties of quantum states is fundamental to the development of quantum technologies. So first of all, in quantum computing, we need to know the state of the quantum processor to make sure it's working as expected. So if there are errors in the quantum gates or the coherence, we need to be able to detect the errors in order to correct them, right? So in quantum communication, if we are using states to transmit information, we must be able to characterize the states we are sending to ensure we are sending the right states and that the transmission of information is secure. So for example, in device-independent quantum cryptography, if the states of the system that we are sending are compromised or mischaracterized, the security of these protocols might be at risk. And finally, there is also quantum metrology, and this area relies on precise measurements for measuring physical quantities using quantum properties. And then, in this case, quantum state characterization helps ensuring we are preparing the right states and we are generating the right amount of entanglement, which is crucial for technologies that depend on extreme precision. So basically, by characterizing quantum systems, we are ensuring the reliability of these systems over many applications. And then we can verify our experimental setups, find errors, improve the performance of systems, which is fundamental to many of these technologies. Okay, so there are different techniques for obtaining properties of quantum states, each one with its own advantages and disadvantages, but they all prepare copies of the quantum state, they measure them, and then they post-process the data to obtain some function of the quantum state. So ideally, we want a method that gives us as much information as possible, is efficient in terms of shots or number of copies of the states, use few settings and simple ones. We don't want to use a lot of entanglement, for example, entanglement measurements. And once we have collected the data, the classical post-processing is not very hard. But of course, there is always a trade-off. Some methods gives us a lot of information about the state, but they require a lot of data and very heavy post-processing, while other methods are more efficient, but they only give us partial information. So, of course, there are many techniques, but in this talk, I'll focus on two key techniques that are very important: quantum state tomography and direct fidelity estimation. So, quantum state tomography is the standard method for reconstructing an unknown quantum state. And the idea here is simple. We measure the system in different directions of the space of matrices and use those results to reconstruct the state. So we get the full density matrix that represents the state of the system. So the main advantage of quantum state tomography is that it gives us a complete description of the quantum state. And this is useful when we need detailed information about the system, because here we are obtaining everything can be obtained about the quantum state, right? And I guess the biggest challenge with quantum state tomography is that it scales poorly. So as the system gets bigger, the number of measurements needed grows exponentially with the number of parties in the system. And then this quantum state tomography is impractical for large quantum systems. Also, we have the problem of the classical processing of the data that we obtain, because we need to store and process a matrix that is exponentially large. All right, so in direct fidelity estimation, instead of reconstructing the full state, sometimes we just want to know how close a given target state is to some experimental state, for example, to check we are preparing the right state in an experiment. I don't know. And this is what direct fidelity estimation does. So instead of measuring all Pauli strings that are informationally complete for a certain dimension, what direct fidelity estimation does is randomly selects specific measurements that are relevant to the estimation of the field. So the big advantage of this protocol is that it's more efficient, right? Since it requires fewer measurements than full quantum state tomography. But direct field estimation only works when we already have a reference state to compare against. And then it only gives partial information about the system. The only thing we know after we perform this protocol is the fidelity of the experimental state with respect to a target state. And also, while this protocol requires fewer measurements than quantum state tomography, the efficiency of the method depends on the state being analyzed. It depends on the target state. So for some states, it's very efficient, but for some other states, it's still exponential. So as a summary, quantum state tomography gives us full information, but it's costly, while direct fidelity estimation is more efficient, but only gives partial information.
So Leo, I have a simple questions. So can you go to the earlier slide?
Yeah.
So you see, you told that, okay, obviously quantum state tomography, in case of the quantum state tomography, you don't have any reference state. So that's why you
No.
have to do a informationally complete measurements.
Yes.
Whereas in the direct fidelity estimations, you can do the direct fidelity estimations only when you have the reference states, right?
Yeah, because direct field estimation, you have a target state or
Exactly.
something, a state,
Exactly.
and you
Exactly.
have an experimental state, and you only want to know the fidelity between these two states.
Exactly. So basically, so that means when I was when I was doing state tomography, I am doing sigma x, sigma y, sigma z, these three measurements. But when I'm doing direct fidelity estimations with the reference state is one of the eigenstate of sigma z, then I'll only perform sigma z measurement, right?
Uh,
The kind of things, right?
yes, yes, but this is mostly done for high dimensional systems, right? If you have 10 qubits, you cannot measure all the Pauli strings that act on 10 qubits. But in the case of direct field estimation, you only sample a subset of those or of all those Pauli strings. So instead of measuring 1 million, I don't know, 1 million Pauli strings, like in quantum state tomography, you measure 1,000.
I see. Okay. Okay. I mean, it scales very, I mean, for the higher number of qubits, the scaling is abruptly changes in the direct field
Yes,
distributions.
yes, it's exponentially faster than quantum state tomography.
Okay. Okay.
Yeah.
Thank you.
Yes. Yeah. So depending on the situation, we might choose one protocol or the other, right? Depending on the things we want. Okay. So good. So after saying that, I'm going to talk about these two protocols in more detail. First, about quantum state tomography and two ways of performing quantum state tomography, and then about direct fidelity estimation with an example, and if we have time, about some improvements to this technique that we did with my collaborators here at ICFO with Julia and Maria. Okay. Good. So quantum state tomography is the process of reconstructing a quantum state by performing different measurements on multiple copies of the system. So you take many copies of the state, you measure different operators, you process the data, and what you want is to get this matrix. You want to obtain all the coefficients of the density matrix. So there are many methods of quantum state tomography, but in general, the process has three key parts: the measurements or settings we choose, the data collection, and the classical process. So the first step is choosing a measurement strategy, and here we need to measure different operators, different directions in the space of Hermitian matrices to gather enough information. So the most common approach is to use a set of measurements that is informationally complete. And what this means is that they provide enough data to fully reconstruct any quantum state, because we are measuring a basis of the space of Hermitian matrices. So for qubits, this often means that we have to measure all the Pauli strings for a given number of qubits. So once we have chosen a set of measurements, we apply them to many identical copies of the quantum state. And this is important because measurements are probabilistic. You don't get exactly the same result every time, right? So we need to repeat the experiment enough times to get reliable statistics. We need good approximations for the expectation values we are estimating, right? So the more copies of the state we have, the more accurate our reconstruction will be. And finally, we take all the measurement data and process it using classical algorithms. And the goal here is to reconstruct the density matrix that best explains our measurement outputs. So here there are many methods like linear inversion, maximal likelihood estimation, Bayesian method, compressive sensing, and many other methods. So here we have an example. So this could be the density matrix of an experimental state of a qubit. We measure this state with this PVM that contains all the eigenvectors of the three Paulis to obtain this probability, right? So we collect all the outcomes, we construct this histogram, and with this histogram, we approximate these probabilities. And using these probabilities, we find an estimation of the original state. But this is not exact, right? We see that these two matrices are similar, but they are not equal. And in this case, the error comes because these probabilities are obtained with a finite number of copies of the states. So these probabilities are an approximation for the true probabilities, and then the state, since we use these probabilities to reconstruct the state, this state will never be equal to this one unless we measure an infinite number of copies of the state. Good? All right.
So, Leo, in what platform you are doing this experiment to get this probability?
No, this is just a simulation.
Just a simulation. Okay.
Yeah, it's just a simulation. It's like, yeah, I did it with my computer.
And how many, sorry, can I ask something, Leonardo? So how
Yeah.
many copies do you have to like to get this estimated state?
So in this case, I used like 10,000 copies of the state. Yes. But actually, in this slide, I'm going to give you like the exact value, number of shots of copies of the state you need to get some precision. So if you give me a precision, I can give you the number of shots or copies of the state you need to perform tomography with some precision. Yes.
Achha, I had one question regarding this previous slide. Can I please ask?
Yeah. Sure.
Yeah. So the thing is that is something like this happening? Like when you are taking this repeated measurements, then you are actually for a single qubit state, you are actually trying to estimate the 4 different entries that you have in the matrix. So
Yes.
So that means, suppose by repeated measurements, those sequence of complex numbers that you are getting as the entries are getting converts to particular number.
Yes. So you increase the number of shots, you increase the number of copies, and then these will converge to these other numbers. Right? But in principle, you need an infinite number of copies to get exactly these numbers. In practice,
we need, but the thing is that if suppose I take a very large number of repeated measurements, then by looking at the pattern of the sequence that I'm getting for the entries, will it be possible to say that this will be the limit of the sequence?
No, you cannot, because it's like so what these probabilities are giving you is like a set in which the quantum state can be, right?
Okay.
And then when you are increasing the number of shots, you are decreasing the size of this set.
Yes.
But then this set will never be 0, right? So for example, if you have a dice, for example, you have a dice and you do the same. You throw the dice many times, and from the histogram, you want to estimate the probabilities of the dice. You will never get 1/6, right? 1/6 for the dice.
I will never get 1/6, but what I'm trying to say is that by looking at the pattern of the sequence, will I be able to say that this can be the limit of the sequence, at least in some of the cases, so that I can get those entries over there? Because these are basically sequences of complex numbers that you are generating by repeated measurements.
Yeah, but it's like, so what you can say is that the state that you get is epsilon close to the exact state, right? But how can you be sure that this is a 2 and not a 2.00000001 or something like this, right? You can never be
Yes.
sure that.
That is what I'm saying. There will be of course, I will become close to an epsilon distance over there. At least we can say that. That is what we do in any limit that we are trying to do. So yes, that is that epsilon neighborhood that we can say over there.
Yes, the epsilon will never be 0. Yeah. So
That
actually there
epsilon,
are.
no, that epsilon will never be 0, because for that we need infinite number of measurements.
Yes, true.
Okay. Fine. Okay.
Yeah. Okay, so one of the simplest ways to do quantum tomography is through linear inversion. And so here the idea is straightforward. We perform many measurements on different copies of the system, collect the outcome probabilities, and then we solve a system of linear equations to estimate the states. So this is based on the Born's rule, right? The probability of getting a certain measurement outcome is given by the trace of the product of the density matrix with the measurement operator. So here we assume we have a quantum state in dimension D and a PVM that is informationally complete, which means that the operators that compose the PVM form a basis for the Hermitian operators that act on dimension. So every Hermitian matrix can be written as a linear combination of the PVM elements when we have an informationally complete. So when we measure the state with the PVM, each outcome of the PVM has a probability pi equal to this, to the trace of the product, of the state, and the PVM element. So this product can be expressed in vectorized form, where we map matrices to vector by stacking one column of the matrix on top of each other, like in this example that we have here. So we have a matrix of 2 by 2, and then we get this vectorized form of the matrix, putting the columns one on top of each other. So these two things are equal. So the dot product between two vectorized matrix is equal to the trace of the product of the matrices. And this is true for any matrix. You can do this with any square matrix. Right? So
Leo,
Leo,
in the vectorizations, it would be will it be omega W, Y, X, and Z?
yeah, right. Yes. So there are two conventions in vectorization. You can put one row on top of each other or one column on top of each other. So these are conventions, and I guess
both are fine.
Yeah, you can choose one convention or the other. You will get the same result as soon, but you have to be consistent. Yeah, sorry. Yeah. Yes. But for the columns, you will have to put, then this would be Y and this would be X. Yeah. Sorry, I made a mistake here. I mixed the conventions. Yeah. Okay. Okay, so this is true for individual probabilities. The vectorized form of this equation here. But now we can get, since we have all these probabilities for all the outcomes of the PVM, we can get a system of equations like this, where this matrix A is a matrix containing information about the measurement operators. So this is the matrix A, and each row of this matrix would be the vectorized form of the PVM. Rho is the vectorized form of the density operator, and this P is the vector of probabilities, and these probabilities can be estimated from the histogram of outcomes, right? So we prepare many copies of the state, construct this histogram of the outcomes, normalize, and these will be the estimated of the probabilities for each one of the outcomes of the PUE. So this, what we see here is what is written here on the right. So this is the matrix A, this is the density matrix, and then you see that when you do this product, you get this is equal to the probabilities. Now, this is the system of equations that we get, and now A is a matrix that we know because we know the PVM that we are measuring. We know the settings or the operators that we are implementing in the experiment. P are things that can be obtained experimentally, right? From this histogram. And then you can invert this system of equations to obtain an estimation for the density matrix that is in the system. And this product of matrices that you see here is the pseudo inverse of this matrix A, right? So this is a way of doing quantum state tomography. You have this system of linear equations that is given by the Born rule, and then you find the inverse of this system of equations. Okay, and here you see that this matrix will never be equal to the matrix that we have in the experiment, right? Because these depend on the estimation of these probabilities. And since we are estimating probabilities with a finite number of shots, these probabilities will never be equal to the trace of the density matrix times the PVM. So these matrix will always have some error. Yes. And this error will depend on the number of, on how good we estimate these probabilities, and then will depend on the number of shots or copies of the state we use. All right, so so we have an estimation of the density matrix, and a problem that we might get is that the estimated density matrix is not physical. So it could have negative eigenvalues, meaning that it's not a proper quantum state. Then what we have to do is to project this solution onto the set of density matrix. So we have to find the closest density matrix to our linear inversion solution. And we do this by solving this optimization problem. So here we have the solution that the previous step of the tomography gave us, and then we find the closest proper quantum state to this solution that we have. Right? And we can do this with using convex optimization or with optimization.
Leo, you are using the Frobenius norm over here, na, for that minimization?
Yes, the Frobenius norm. Yes. Because with the Frobenius norm, we have fast algorithms, but in principle, you could use other norms also. Right.
Okay.
Yes.
Okay, Leo, I have one query just because, okay, this experimentally achievable, this rho need not to be state, right?
Yes.
So
Well,
actually,
the thing in the experiment is a state, but the solution of the inversion, since we have noise, might not be a state.
Exactly. So actually, what property of state it lose actually?
The positivity. You might get negative eigenvalues.
I see.
These
Okay.
things. Yeah.
Leo, another question. I mean, this happens because this matrix A, it doesn't have inverse, right? I mean, you have to take the pseudo inverse, right? In general, like what you get from the experiment. So is this the reason?
No, I think the probability. So each quantum state, when you measure it, gives a probability distribution, right? But not every probability distribution is associated to a quantum state. So then, since this is an approximation of the actual probabilities, then if you use this approximation and you multiply this approximation by this to get the state, you might get things that are not states, right? Because this probability might not be associated to any quantum state. Yeah. So it's because these probabilities, when we estimate these probabilities, we always have error. Yes.
But then if it does not have negative eigenvalues, but still it could not be the state that we actually used in the experiment, right?
Yeah. Yes. So what you get here is a state that is close to the state in the experiment. So actually, if you want, if you this is the experimental state, and this is your final solution after doing this projection. So if you want that the state of the experiment is no, actually, if you want that the state of your estimation is close, epsilon close to the experimental state, you need to measure a number of shots or copies of the state that is larger than this one, right? So you have you need a number of shots that is larger than the dimension cubed over epsilon squared, and this is some confidence.
Yes, yes. But you see, in this minimization, this row that you are minimizing over, it is not the experimental state. It may not be the experimental state. Right?
No. Actually, I should have put a different variable here. This is a variable. It should be x or yeah. Sorry.
Okay.
Yes. So actually, you will never get the experimental state, but you will get this guarantee. You will know that the state will be at least epsilon close to the experimental state. But you have to use a number of shots that is proportional to the dimension, right? Something proportional to something that is exponential in the number of qubits. And actually, this value that we see here is optimal. You cannot do better than this. So any quantum tomography algorithm that gives you precision epsilon needs to use a number of shots or copies that is proportional to this quantity. Like this. You can get constant improvements or logarithmic improvements, but you will always get something. You will always need something proportional to d squared if you use Pauli measurements like separable measurements.
Leo, I had another question over here. Like you said that when we are doing this estimation, then the estimated state can lose the positivity property. That's why you are using this row projection.
Yes.
So I was thinking of another situation. Like, can this happen that it loses its positivity property, but still it has its Hermitian property? Can it lose its Hermitian property also?
No, it doesn't lose the Hermitian property because the way we are constructing the
okay,
the inverse. Yeah. If you measure Pauli operators, it doesn't lose the Hermitian property, and also it doesn't lose the trace one property, right? Because this probability is someone. So the positivity is the problem.
Okay, thank you.
And this is a difficult problem, eh? Like solving this, sometimes it takes a long time for your classical computer to solve this optimization.
Okay.
Yes.
So Leo, I have one question. So actually, you have used trace one norm. So if you use another norm or some different norm, does that affect your number of copies, or is still?
Yes, it does. So for example, you can use Fidelity, and then that affects the number of copies. You get something that goes like epsilon instead of epsilon squared. Or if you use Frobenius norm, you get you lose a factor of d here or something like this. Yeah, but I guess all norms are some sort of equivalent, right? If something is very close in one norm, should be close in a different norm also, right?
But then in terms of number of copy, they should give same bound, right? Why they are giving different bound? If they are,
yeah, because the norms, sometimes you can say this is upper bounded by the square root of d, the Frobenius norm. So you get factors of d when you do this.
Okay, in that way. Okay,
yes.
I got it. Okay, thank you.
And also this lower bound for this number of copies. So is it tight? Like, is there any way to achieve this thing exactly?
So these lower bounds are like some sort of asymptotic bound. Yes. So you can get logarithmic factors here, improvements, or you can get constant factor improvements. But in the large number of qubits, you will always get this d cubed over epsilon squared. Yeah, if you use these kind of measurements, Pauli's separable measurements, if you use, this is like sequential. If you use a sequential protocol, you measure one state, then you measure another, then you measure another. But if you use a collective measurement over all the copies of the state, so you have all the copies of the state in a quantum memory, and you measure all these copies at the same time, you can get a d squared. D squared here. You can gain something, a factor of d, but it's still exponential in the number of qubits.
Right. Okay.
Okay.
I had one question.
Yes.
So which optimization technique do you use for this minimizing the distance? Is there any choice? Like, will all the optimization techniques agree the target state to be reconstructed?
So usually you use semi-definite programming because it's very fast and it gives you, well, very fast. Yeah, it's fast, and it also gives you like a certificate. It tells you this is the solution, and you compare to the solution. So if you use gradient descendant or other techniques, you might not know when to stop the optimization. But with semi-definite programming, you know that if you get a number, that is the number.
Okay, but in general, they may not agree, right? Any like maximum likelihood estimation or SDP, they may not agree on the level of reconstructed state.
Yeah, they might not agree. Yes, they might not agree.
So is there any specific reason that you will choose one over the other?
So, so this is one post-processing method for the data. You have the data, and then with this method, you get an estimation for the state. And the advantage of this method, linear inversion, is that in this paper, they showed these numbers that you have here. Right? They show that if you want precision epsilon, you get this. You need this number of shots. If you use other post-processing techniques like maximum likelihood estimation, you might not know how many shots you need to reach certain precision. It's like, yeah.
Okay. So in their calculation, do they assume that the measurements are all perfect, or there is scope of error in the measurement?
Yeah, they assume the measurements are all perfect. You know exactly the PVMs that you are measuring.
Okay, so there are no readout errors or any such errors.
No, not any sort of. Yeah. This is in the ideal case where the only source of noise you have is the shot noise, the noise that you have when you don't have the full statistics of the.
Yeah, so I don't have basically the true probabilities. I have some statistical.
Yes. Yeah.
Okay.
Okay. So, yeah, maybe I'm going to skip this slide because we have 40 minutes in the presentation. So this was a method to perform quantum state tomography, but this method, or actually any method of quantum state tomography, scale well with the number of qubits. So the reason of this scaling is just the number of parameters of a quantum state, right? So for a single qubit, you have 3 real numbers, right? The parameters in the block sphere. But for 10 qubits, you have more than 1 million parameters, real numbers that you have to estimate. And then quantum state tomography is very difficult. So this exponential number on the parameters means 3 things. So the number of settings or different bases or different Paulis that you have to measure grows exponentially fast. Also, if you increase the number of qubits, we need exponentially more copies of the state, right? Because we need many samples of this state to get accurate statistics to estimate these probabilities well, and in that sense to get a good reconstruction of the state. And also we need exponentially more computational resources, right? Because we have to process all this data, all this huge matrix that is exponentially large. And we also have to store this exponentially large matrix. So actually, there are rigorous results that validate this. So actually, any quantum state tomography algorithm, if I want to estimate the state with a fidelity 1 minus epsilon, so I want to be 1 minus epsilon precise in the fidelity, I need at least this number of copies, where this is the rank of your quantum state, and this is the dimension. So we need something proportional to the dimension, which for qubits is exponential. And this is very, very, very interesting. So any method of quantum tomography that you could design or propose is going to need at least this number of shots in the asymptotic limit if you want precision epsilon. So for any method.
So does does this estimation come from some fundamental limits or something? What is the why it is this way? Like why is it?
Yeah. So what you do to demonstrate this kind of limits is to use techniques from information theory. So you map the problem of tomography to a problem of communication. So I want to send you information to a quantum state. And then there are limits that say how much information I can send, right? There is I don't know, Fanos bound. And then you use these kind of techniques to show that you cannot estimate states using less shots than this amount in the asymptotic limit. Yeah. So yeah.
Okay, so in that way, it will violate some communication principle, like something like. Okay.
Yes. Yeah. Yes. So because of this, full quantum state tomography is only feasible for small systems, maybe 6, 7 qubits in a real experiment. But for larger systems, you need smarter techniques. So one of these techniques is direct field estimation, and the motivation here comes from the fact that sometimes we don't need to know everything about the state. We might just want to know the fidelity of this experimental state with respect to a target state. So this is what direct field estimation does. Instead of reconstructing the entire state, direct field estimation estimates just one number, the fidelity between a given target state and your experimental state. And the key advantage is that direct field estimation, this protocol requires far fewer measurements than tomography. And then this is ideal if you want to benchmark quantum devices and checking if you actually prepare the state that you wanted in your experimental system. All right, so the quantity you want to estimate is the fidelity that is defined by two quantum states, rho and sigma, like this. And if at least one of the states is pure, the fidelity simplifies to this other quantity. So the fidelity goes from 0 if the states are totally different to 1 if the states are identical. So for direct field estimation, we need to express the quantum state as a linear combination of Pauli strings. So actually, any state or any Hermitian operator can be written in this form, where these are some real coefficients, and these are Pauli operators, Pauli strings. And these coefficients are basically the expectation of these Pauli strings over the states. Yes. So with this representation, you can write the fidelity between two states in this form. So if you want to calculate the fidelity between rho and sigma, the only thing you have to do is multiply these two quantities. It's the sum of the product of these coefficients. Okay, so this representation of the fidelity is important because if one of the states is pure, let's say rho, be associated with the b coefficients, then the sum of these b squareds is 1. And then we can multiply and divide this fidelity by b, k, and we get this expression that we see here. And then we can think the fidelity between these two states as the expectation value of a random variable x that is given by these things here. Right? That and this random variable follow this probability distribution bk. So the fidelity now can be thought as the average of this random variable x. Okay, so then we know from the central limit theorem that if we sample values of this random variable, we sum all these values and we divide by the total number of variables that we have. In the limit of large L, this sum will converge to the fidelity, to the actual average. So the sample average will converge to the average of the distribution. Okay. So any question here?
So Leo, so basically this is you're calculating trace of rho and sigma, right? Because if one of the state is pure, then you simplify the expression of fidelity, right?
Yes, actually this is true for any state, but if one of the states is pure, you have this property. You have that the sum of this coefficient squared is 1, right? And
Yes.
if the sum of something is 1, then and this thing is positive, then you can think this is a probability distribution.
Yes, I mean, just go back to your previous slide.
Mm-hmm.
Yes, for example, like the first expression, what you have, this rho and sigma, if they are a mixed state, then this is the expression. If one of the state is pure, then this is the expression, right? Trace of rho and sigma, right? So once you assume that one of the state is pure, then the things simplify, right?
Yeah, the things simplify because you have that the sum of these things squared is equal to 1. Yeah.
So, I mean, here this idea is this, let's say you want to run something on quantum computer. I mean, because ideally we want to run something, some unitary evolutions, and you start with ground state or something. Then you know at the end it should be a pure state. Is this the idea? Like, and then because of the noise, it get mixed, and you want to estimate the your target state is a pure state, and you want to estimate the fidelity between your target state and your mixed state. And
yes,
this is the way you want to quantify the noise. Is this the idea?
Yes. So you have the target state that you know. This is something you know because you calculated or whatever is the thing that you want to prepare. And you have the experimental state. And you want to get how far away are these two things.
Right.
To check the quality of the preparation also. Yes.
Right. Okay.
Okay, so in the protocol, we have a target pure state, this rho, with coefficients b that we know. So we know these coefficients, and some experimental quantum state sigma. And we want to get the fidelity between these two states. And we don't want to do quantum tomography. Because with quantum tomography, we could do this, but we know that it's expensive. So the first thing we have to do is to construct this probability distribution. So we can sample these values from the experiment. Remember, the values bk we know, and the coefficients ak we can obtain these values from the experiment, calculating the expectation values of Paulis. Yes. So first, I'm going to give you the protocol to estimate this fidelity, and then I'm going to give you an example of how to do it. So the first thing, so this is an experimental protocol, and then you have an error and you have a confidence. So the first thing you have to do is to choose the error level. So you want to say that the fidelity is the fidelity that you get is close to the true fidelity between these two states, and the confidence 1 minus delta. So you want to say, I don't know, the fidelity that I will get, it will be at most 10 to the minus 2 far away from the exact fidelity the 99% of the time, right? So you choose these two parameters, and these will give you the number of settings you have to measure in the experiment. So if you want more confidence and less error, you will have to measure more things in your experiment, right? This is reason. So, for example, if you want to error in the fidelity of 10 to the minus 2 and confidence 99%, you need to measure around 1 million settings, around 1 million Pauli operators. Okay. So once you selected the Pauli strings you have to measure by sampling, you have to estimate the expectation value of these Pauli strings using many copies of the quantum states. How many copies? Well, this will depend on the error we want, the confidence we want, and also on these coefficients pk. So this is the number of copies we have to measure for each one of the Pauli strings we sampled in the previous step. So if you do this, if you estimate the expectation value of these Pauli strings, you will get the value of the coefficients ak that you selected randomly. Remember, you selected these coefficients randomly in the previous step. Then you sum all these values and you divide by the number of Paulis that you measure, and this will give will be the estimator for the fidelity. So yeah, basically this is the protocol. You sample random Pauli strings, you estimate those random Pauli strings in the experiment, and then the sum of all these things, the sample average of all these things will be the estimator for the fidelity. And in this case, you will have an estimator with error at most epsilon. And for this, you will use an average at most this number of copies of the states. And this will depend on your target state, because for some states, these don't depend on the dimension, for example. And here you see that this method is much faster than tomography, because if you do tomography and you want to estimate a fidelity, you will get something that goes like d squared number of copies of the state, and here you gain a factor d in the number of shots. And yes, so this is more efficient than calculating the fidelity with direct fidelity estimation is more efficient than calculating the fidelity using quantum state tomography. You need less shots. Okay, so instead of giving you a demonstration of the protocol that is a bit technical, I want to show you an example. So how you would use the protocol to estimate a fidelity. So here we have this pure target state of 1 qubit, and we want to estimate the fidelity of this between this state and some experimental state that we don't know, right? So what we do first is we express this state as a combination of Pauli strings. As we see here, this is for 1 qubit. Then from these coefficients, we construct a probability distribution, this probability distribution that we see here, and choose an error epsilon and a confidence 1 minus delta, right? So here in this case, choosing this number, we are saying that the error in the fidelity is at most 0.1, and the confidence and the result that we will get will be true the 90% of the times. So if we choose these parameters, we have to measure 1,000 random Pauli strings. And which Pauli strings? Well, the Pauli strings that we sample. So in one run of the protocol, we would have to measure we could have to measure these Pauli strings, for example, like identity X, then identity, then Z, then Y, X, whatever. Fine. Sampling from this probability distribution, this values. Now, this is the second step, and now we have to estimate the expectation value of these Paulis in the experiment. And the number of copies of the state that we have to use to estimate these values will depend on the policy. So in this case, for these states, for example, the X Pauli needs to be estimated with 2 shots. The Y Pauli needs to be estimated with 2 shots, but the Z Pauli needs to be estimated with 4 shots. So in this case, the Z Pauli needs to be estimated with more precision than in the other two, Paulis, and this depends on the target state that we choose. Okay, so once we do that, once we estimate these expectation values in the experiment, we sum all these things and we divide by 1,000, and this B will be this B that are here, right? So I will be 0.43, and this will be the estimator of the fidelity between my target state, this target state, and some experimental states unknown. Yeah. So
I have another question. Can I ask?
Yeah, sure.
Yeah. So, like, I mean, in general, when people implement this method in experiment, they also like do the measurement error mitigations, because when you apply this Pauli, I mean, I understand this is a single qubit measurement, right? Like you have, I mean, it is less noisy, that is for sure. But I mean, because the problem is like in the fidelity, like, I mean, there is two kind of error. Like one is the error coming from your process, like your process is not unitary, it's something noisy. And there is another error coming from the measurement error. And I suppose it's not possible to distinguish between these two kind of errors. I mean, in the protocol. I mean, am I right?
Yes, actually, yeah, this is also ideal. This is the protocol assuming you don't have any error in the measurements. If you measure Pauli X, if you want to measure Pauli X, you are sure that the thing that is in the experiment is Pauli X, or is something that is it has very low noise, right? You don't have readout error or this kind of thing. Okay. Yes. So this protocol and the guarantees that it gives you are valid for the ideal scenario where you only have short noise. Yes.
Yes.
Then if you have a readout error, I guess you have to add some, to modify the protocol, to add some other, this epsilon would be the epsilon from the short noise plus the epsilon from the readout error or something. Yeah, you would have to modify the protocol.
Yeah, I mean, no, I mean, do the people use this measurement noise mitigations? Like you can have this matrix, right? This measurement matrix, and you do the pseudo inverse of your result, like of your strings. I mean, I think it should improve, right? This measurement error is not that problem, as I understand. Like it is possible to mitigate.
Yes, but then because this is the technique, but the technique has a demonstration, and I guess you would have to modify the demonstration if you want to include these techniques, the error demonstration, the error mitigation techniques. But I guess it can be done, right? So you will get the noise of the short noise plus some other component that comes from the fact that your measurements are noisy or whatever.
Yeah. I mean, for example, this randomized benchmarking, like the protocol that you were describing, it has some overlap. Like the randomized benchmarking does the same kind of job, like the quantify the noise. But this randomized benchmarking is actually robust against this measurement and state preparation error, because I mean because at the end it will give you the average gate fidelity of your gate of interest. So yeah.
Yes. Oh. So I guess randomized benchmarking is more robust, but it also gives you less information, right? because
Yeah, I agree. I mean, it has its own problem, like because you cannot, people don't know how to yeah, use this method for beyond 3 qubit, because preparation of Clifford gate is not something is easy. So this method is something cool because you don't prepare some special thing. You just have this Pauli string measurement. So in that sense, this is more scalable than randomized benchmarking for sure.
yes, 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 yes. Yeah.
Yes. Okay.
Okay, so this is the example. We did some improvement of this method with here at ICFO, but yeah, it has been 1 hour. So I'm going to conclude now. So what I can say at the end is that quantum state characterization is crucial for quantum technologies, right? But traditional methods, in particular quantum state tomography, are not scalable. However, if we want to know more specific information about the state, there exist better methods, and well, direct field estimation is one of these more practical methods. So depending on the scenario, we need to be careful to choose the right technique to balance the accuracy we want, the efficiency, and the feasibility. So thank you for your attention.
Yeah, thanks a lot. Can we just go back to your previous slide? I have some technical questions. Yes, maybe here the improvement. So, I mean, what kind of noise you are assuming to in your protocol?
Noise. The only kind of noise is the shot noise. So the only uncertainty you have is the uncertainty that the fine statistics give. Yes. 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 So you don't have actually. I think that has not been done like this. I'm not aware of any paper that tries to connect this direct field estimation protocol with uh, noise in the measurements, right? Read of noise or something. I'm not aware of any protocol.
Yeah,
Maybe
I mean, for example, let's say, I want to do some operations, some immediate operations, and I know that like my target state is a pure state, okay, and then I have a simple, okay, depolarizing noise. I mean, can I connect this your direct fidelity estimation with the depolarizing noise strength? Is it possible?
I guess you can, yeah. I guess you can. But probably if you want to estimate a depolarizing channel, there must be more efficient methods, right?
I mean, yes, like randomized benchmarking can do this thing, but the problem is, I mean, like for me, the method that you were describing, it doesn't matter if you have a big, 10 qubit circuit. Maybe you have to take more like Pauli measurement, but at the end you will have the direct fidelity estimation, right? Using this method, it should not matter if the number of the qubit increase, right?
Yes. Yeah, I guess you can using this protocol for sure you can estimate this parameter, right? You only have to estimate one parameter, and that parameter can be estimated from the fidelity. If you assume that your noise is a depolarizing channel, right? You have to make that assumption. Make that assumption.
Yes, I mean, because this is simple to handle here. Otherwise, yes, yeah.
Yeah.
Okay. Thanks a lot.
Thank you.
Okay, thank you, Leo.
I one question that hi Leo, and thanks
Hi.
for the nice talk. And I have just question that instead of measuring separately, if you perform an entangled measurement, then it will give you more advantage. I mean, maybe it will
Yes.
require less number of sample or something like that. Then the
Yes.
bound will be changed, right?
Sorry,
It
what?
will be very. Then that bound will be changed, right? The order of number of sample you need, that minimum number will be reduced, right? If you perform entangled measurement,
Yes. 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 Yes.
it will be a little bit of I just want to add another comment that it will be a little bit of counterintuitive because it's something like metrology, right? And in metrology, if you perform entangled measurement, then it will not give you more advantage. Actually, that has been shown by McConnell. That instead of preparing your probe state in a separate way, you can prepare your probe state in an entangled way, and that will give you the optimal bound of metrology, which comes from the Fisher.
Yeah.
So here why you think that the entangled measure will give you much advantage? Because it's something like metrology, what you are doing.
Yeah. So actually, for example, if you allow, so in quantum tomography, I show you this bound d cube over epsilon square. Actually, this
Right.
d cube is for entangled measurements, right?
Okay.
For separable measurements, you get a slightly larger factor. So yeah, the demonstration says this. You can do the math and you can show, okay, if I have d cube with entangled measurements, if I have entangled measurements, I need d cube. If I have separable measurements, I need something larger than d cube, I think. Also, if you have entangled measurements, you could use a different protocol, like classical shadows, for example. And in classical shadows, you don't have this. If you want to estimate fidelity using classical shadows, you don't have this factor of the dimension.
Okay.
So you can estimate fidelities using that protocol in with a factor that doesn't depend on the dimension. So you can estimate fidelity of 1,000 qubits, and the thing won't scale with the dimension, I think.
But can you do, sorry to interrupt, but can you do shadows, like using shadows, can you do fidelity estimation for arbitrary states, or is it only?
Yes. Well, you need to be able to represent those states efficiently, right? Because you have a target state, and then you need to, in terms of the number of copies, you can do it, but you also have to store the target state in your computer, right? And then
Yeah, that's why it's usually done with GHZ or like Clifford states, no?
yes.
Okay, thanks.
So here, basically, in metrology, what people try to do that if you have n number of samples, then how much fidelity you can achieve, and there is a fundamental limit called Heisenberg limit. And here you are solving the opposite problem. If you need this much of fidelity, then then what should be your minimum number of measurements? Something like that, right? So here also this minimal number of measurements should be linked with some fundamental restriction of quantum theory, like Heisenberg limit or something like that. These two can be combined, right? There should be
yes. I guess yes. There are like several recent papers that say, I don't know, if you want to get tomography with this precision, you need this number of shots. If you want to estimate the purity with this precision, you need this number of shots. If you want to estimate the unitary, like lower bounds for these things. Several papers. Yeah.
Oh, thanks.
Thank you.
I was wondering whether people use this direct fidelity estimation for process tomography also, or is it only for state tomography?
I guess you can use it for process tomography. Yeah. In the original paper, they talk about this a bit. Like they say that this can be extended to process tomography. Yeah. Because you have like the Choi matrix, right? That is state based.
Okay, thanks.
Thank you.
Okay, Leo, thanks a lot. I'm not going to ask you any more questions today because it is already more than 1 hour. Again, thank you for this nice talk. Yeah, it's lunchtime. Okay. Okay, bye then. Bye, everyone.
Bye.